go through our lesson on quantitative force diagrams. This is going to touch on what we did on Friday, where we learned how to calculate an actual amount of force based off of the mass of something. So if we're successful by the end of this lesson, what we'll be able to do is draw what's called a quantitative force diagram. Now, I believe I've said this word before and we've mentioned what quantitative means, but I'm just going to explain again to make sure everybody knows. Quantitative comes from the word quantity, which is really a word for amount or a numerical value. So in our diagrams now, we're going to have vectors with numerical values associated with them. So not only are we going to look at the length of our vectors, but we're going to look at the actual numerical value that goes with them to see if they're balanced or unbalanced. We're going to do this by calculating the force of gravity acting on objects based off of their mass. And if we're able to do this, we're going to be able to apply this skill to something we did way back when. In the very beginning of the class in Unit 1, we did this spaghetti bridge lab. And our whole goal of that lab was to describe the strength of the bridge in terms of the number of marbles that could be held per strand. Well, now we're going to be able to describe the strength of the bridge in newtons or in force. So after we've gone through the lesson, your exit ticket is going to relate back to that spaghetti bridge lab, and you guys are going to go back and find the force that the bridge can hold. So, moving on. Let's talk about finding the force of gravity. Now, there's two different ways that you can find the force of gravity, and it really depends on your mass. So, if you have the mass of an object in grams, what you can do is you can take that mass and divide it by 100, and that would get you your force in newtons. So our units for force are called newtons. The abbreviated version of that is just capital N. If I wanted to take my mass in grams and I divided it by 100, the unit that I'd have left is newtons. If I had a mass in kilograms, now kilograms are 1,000 times bigger than grams. Instead of dividing my mass by 100, I would take that mass and multiply it by 10 to get my force in newtons. So let's do two examples together to make sure that you've got it. So let's say I had a 15-gram weight and I wanted to know what is the force of gravity on that 15-pound weight. To find my force, I take 15 grams, divide it by 100, and that would get me 0.15 newtons. So not too bad. Let's say that I had a weight that was 25 kilograms and I wanted to figure out what the force of gravity was. I would take 10 and multiply it by my weight in kilograms. So 10 times 25 would get me a force of gravity of 250 newtons. So just be prepared if you have a mass in grams or kilograms how to find your force of gravity. Moving on up to the next page. Now we're going to take that skill and we're going to use it to draw a full quantitative force diagram. So let's look at this first example. We've got a 2 kilogram cart. I'm going to highlight that. So go ahead and highlight this with me. Got a 2 kilogram cart that is pushed with a 12 Newton force. If the cart is accelerating, what could the possible frictional force be? Draw a quantitative force diagram for the cart. So notice I've been asked a question and I've been given the task of drawing the force diagram. Drawing the force diagram is going to help me answer this question about my frictional force. So I'm going to start there. So if I'm imagining this correctly, I've got a cart, wheels, boom, 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 cart with wheels. It's got the little bar. There's a person who's pushing the cart that way, let's just say, because they didn't really give me a direction, so I have the freedom to choose. So this 2 kilogram cart is getting pushed with a 12 Newton force. I'm just drawing a diagram to help me before I go straight into my force diagram. So what I'm going to do is I'm going to represent my cart as a dot, and I'm going to draw what are all of the forces acting on my cart or this dot. So I know for sure that there is a 12 Newton force to the right. Now the type of force is an applied force. I'm going to abbreviate applied APP. And I know it's coming from the person onto the cart. And it is 12 newtons in magnitude or in length, we could say. Now I know that there's also gravity because the cart is on Earth. And there will be a gravitational force, so I'm just going to abbreviate that FG, and that is the Earth acting on the cart. Now I can actually calculate the amount of force by taking my mass and multiplying it by 10 because it's in kilograms. So 10 times 2 kilograms is going to get me a force of 20 newtons. So this force of gravity right here is 20 newtons. Now this gives me a little bit of insight because I know the cart is accelerating, but if I have personal experience with carts, I know that they're not accelerating up into the air or down into the ground. So vertically, my forces are going to be balanced. So this force of gravity is going to get balanced out by an upwards force coming from the ground. Now we call that force a normal force because it's perpendicular to the surface of the ground. So this is going to be the ground on the cart. Now since these forces are equal, they're balancing each other out, I can safely say that this force is 20 newtons. Now on Earth we usually have friction, and the fact that they asked me about friction tells me that there is a frictional force. The thing that I'm going to be careful with is that they also told me the cart is accelerating. So this means that left to right my forces are unbalanced. So I'm going to label my force of friction, yes, friction coming from the ground on the cart, but I'm being careful to draw that it's shorter or less magnitude than my applied force. So this is my complete diagram. I've labeled everything as best as I can. I can't assign a number to friction unless it's been given to me. I don't know how to calculate it. Someday you'll learn, but not today. So now I can answer this question, what could a possible force of friction be? Well, as long as my friction is less than 12, my cart is going to accelerate. So the answer to this question is any number less than 12. If it was 11 newtons, that would be fine. If it was 10 newtons, that'd be fine. If it was 1 newton, that'd be fine. And if it was 0 newtons, that would be fine. Because as long as this frictional force is shorter than my applied force, the cart is still going to accelerate in the direction it's being pushed. So let's move on to a simpler example. We've got a 35 kilogram child that's being pulled on a sled at a constant velocity. Constant velocity tells me one very important thing. It's not accelerating. So my forces are going to be balanced in this scenario. What must the force of friction be if the child is pulled with a force of tension of 40 newtons? Draw a quantitative force diagram. So I'm going to draw my force diagram for the child. I can do a quick sketch here. I've got a sled. Boom shakalaka. I'm not the best drawer. Yay, happy child. It's being pulled by a string, I'm assuming. So this child is 35 kilograms. I think that's a normal amount. I'm not sure if that's a normal amount for the weight of a child. But we'll go with it. So 35 kilogram child, I'm going to represent him with a dot instead of drawing the picture. I know that he's on Earth, so I know that there's a force of gravity, and this is the Earth on the child. And I can calculate the force of gravity by taking that child's mass, 35 kilograms, and multiplying it by 10. When I do that, I get 350 newtons. So my force of gravity is 350 newtons. Now the child's going at a constant velocity, so this means all of my forces are balanced. So force of gravity is going to be balanced out with a vertical force. Now that's coming from the ground. Actually, is it coming from the ground? Is the child touching the ground now that I think about it? No, he's not. He's actually touching the sled. He's sitting in the sled. So the sled is a surface, so I can still call this a normal force, but it's not the ground on the child, it's the sled on the child. So be careful when you're labeling your forces. It does matter where they're coming from. So the sled is acting on the child, and I know that this force is going to be equal to gravity, so this is going to be a 350 Newton force. Now, they told me that the force of tension is 40 newtons. Now, I know I'm not drawing this to scale, but that's okay. So my force of tension, this is the rope on the child, is 40 newtons in magnitude. Now, my friction, I have to think this through. Last time, in the last problem, I knew the cart was accelerating, so I knew friction just had to be smaller than my applied force. In this case, my object or my child is going at a constant velocity, so I know that my forces are balanced. So friction is going to have to balance out that force of tension. So the friction from, and this is not even the ground on the child, because once again, the child's not touching the ground. This is friction between where the child is sitting on the sled. So if the child was sitting on a really slick sled, there might not be friction, but maybe this is a cloth sled or there's a blanket in there or something that's providing a lot of friction between the child and the sled. But this force of friction is going to equal my force of tension, which means it has to be 40 newtons. So this is my complete force diagram, and in doing the force diagram, I've answered my question that I've been asked: what must the force of friction be? It's not what could it be, but what must it be? It has to be 40 newtons, no more, no less. If it was more than 40 newtons, the child would be slowing down. They wouldn't be accelerating. They wouldn't be going at a constant velocity because friction would be greater than your force of tension. If the force of friction was less than 40 newtons, then the child still wouldn't be going at a constant velocity. They'd be accelerating and speeding up because tension would be greater than friction. So if I want this constant velocity condition they've described, my forces have to be equal and balanced. So let's move on to the next slide. Now, these are a couple of tries, so what I'd like you to do is pause the video and try the first one by yourself, and then unpause the video to check your answer with mine. Alright, if you're listening, I'm assuming that you've tried the first one and you are ready to check your answer. So, we have a 25 kilogram suitcase that's pushed onto a conveyor belt with a 12 Newton force. Assuming the suitcase was pushed at a constant velocity, draw a quantitative force diagram. So, we've got, I'm going to just diagram because I always have to diagram. A 25 kilogram suitcase. That was bad. I'm going to try again. There we go. A 25 kilogram suitcase. It's being pushed onto the conveyor belt with a 12 Newton force. I'm just going to say that way. 12 Newton force. And it is being pushed at a constant velocity. This means it's not accelerating, so all of my forces have to be balanced. So now I feel confident going into drawing the diagram. Gosh, I shouldn't leave myself a whole lot of space, but I'll make it work. So I'm going to draw my suitcase as a dot. And the first thing I'm going to do is draw gravity, because I know my suitcase is on Earth and gravity is a thing on Earth. So gravity, Earth on suitcase. Because my suitcase is 25 kilograms, I'm going to multiply that mass by 10 to get my force of gravity to be 250 newtons. Now the forces have to be balanced, so this means that my normal force has to be equal to my force of gravity. So my normal force coming from the conveyor belt on the suitcase has also got to be 250 newtons. So that's great. Now I'm going to draw my horizontal forces. I'm going to draw them long so that I have room to label them. I know that there is an applied force. I'm assuming this applied force is coming from a person on the suitcase, and I know that this applied force is 12 newtons because they gave that to me in the problem. Since this is happening at a constant velocity, this means this force is balanced out with another force that is equal and opposite. So this other force, the only thing I can think of is friction. This is also coming from the conveyor belt on the suitcase. So if my applied force was 12, that means my frictional force is 12. So hopefully you got the try right. If you did, congratulations. If not, that's okay. That's a part of learning. We learn from mistakes. Go ahead and pause the video and try the next one. All right, if you are listening right now, I'm assuming that you've unpaused the video and you're ready to check your answer. This is my favorite one. It's me, and I'm at the happiest place on earth, Disneyland. I guess that's not, yeah, no, that's accurate. Kind of. I'm at Disneyland, but I'm on the California Screamin' roller coaster, which I don't even think it's called that anymore. I think they updated it. It's like the Incredicoaster. It's really sad. They've gone too far, but that's another topic. But this ride is not even in the Disneyland park. It's in the other park, the California Adventure Park, and I don't even think it's called California Adventures anymore. I think it's called something else. Sad day. But anyway, I'm on that roller coaster, and if you've ever been on this roller coaster, it's amazing because at the very beginning, it's my favorite part. You're like at a standstill, right? And there's all of these people at the pier that are looking at you, like up here. They're like, bye, have fun. Oh, it's gonna be great. And they're like taking pictures and it's flashing and all that stuff. And you're like, yeah, it's gonna be awesome. And there's a speaker in your ear and it's like saying something, I can't even remember, like, get ready, racers, and it's countdown, take off in 5, 4, 3, 2, 1, blast off, or something like that. And then when one hits, you accelerate and you like feel it like in your chest, like in your like gut, like your whole body. You feel your organs like slam like into the back of your body. It's amazing. And you go, I looked this up, from 0 miles per hour to 55 miles per hour, and you do it in 4.5 seconds, which is insane. It's insane. It's a crazy sensation, and it's a lot of fun. So anyway, when you go through this, when I went through this, when people go through this, they experience a 335 Newton force accelerating them, which is awesome. So depending on your mass, this might change your diagram, but let's just say, this may or may not be accurate, let's just say that my mass is 61 kilograms. I'm very vulnerable, so don't go Googling how many pounds that is, okay? Promise. Okay, moving on. So let's say that my mass is 61 kilograms and I experience this force. We want to draw a quantitative force diagram for me, and we're just going to make life simple and assume the ride is frictionless. We know that's not the case, but let's just make it simple. So let's get started. I'm going to represent myself as a dot. I'm going to do it over here because it seems like there's more room. So first things first, there is an applied force on me that is 335 newtons. Now, I can say that it's coming from the mechanics of the roller coaster, the wheels, traction, all that good stuff. But I'm just going to keep it simple and look at what immediately my person is touching, and that is the seat in the cart. So I'm just going to say this is the cart acting on me. You could say it was the seat. It doesn't really matter. But it's 335 newtons. Now, my mass, being 61 kilograms, is going to tell me what my force of gravity is. So my force of gravity is the earth acting on me, and 61 times 10 means it's a 610 Newton force. Now, I'm not accelerating up or down. I'm accelerating to the right. So up and down, my forces are balanced. So my normal force, which is also coming from the cart on me, coming from my seat on me, is also going to have to be 610 newtons. So, that is the force diagram. I believe this is the end of your notes, but I'm going to flip to one more slide that I did not print out for you guys right here. So this is the exit ticket. The exit ticket is online, so go ahead and visit this link. One thing I am going to say is take your time. It's only 3 questions, but the math part of it is pretty heavy. It's going to be worthwhile to draw a force diagram. You're not going to be asked to draw diagrams. You're going to be asked for specific forces and amounts, and it's all going to relate back to our spaghetti bridge. So it's not a times quiz. It's not something I want you to rush through. It's really something I want you to think and problem solve on. So maybe have a whiteboard ready, have a calculator ready, and be ready to just draw a diagram to help problem solve your way through it. After you've submitted that, the homework is going to be this horse and cart quantitative problem worksheet. Once again, take your time, be neat about this, and be prepared to have a calculator because it's quantitative, and it'll be a doozy. It's meant to challenge your brain and really get you to think through the problem. So don't be intimidated if it doesn't seem immediately obvious what the answer or solution is. But I have faith in you guys. Thanks for watching the video, and thanks for being so awesome. I appreciate